Okay, so this is this one. We are currently studying the part of quantization of charge, light, and energy. This includes the quantization of electric charge, okay, Thomson, Millikan, the quantization and measurement of the elementary electric charge E, which is the charge of the electron, and the mass of the electron also, okay, which can be measured in the Thomson or the Millikan experiments, okay. The black body radiation, we also studied this phenomenon. Actually, it is a very normal phenomenon, okay. You still can see it, okay. Any heated body, heated material emits electromagnetic radiation whose maximum wavelength, okay, of the maximum intensity actually depends on the temperature. So you can remember that as you increase the temperature of the material, the more intense wavelength will be at smaller twill. Okay, the maximum, the wavelength of the maximum intensity will be smaller, meaning that you as you increase the temperature, you are going basically from red to blue, okay? The photoelectric effect, I will show it here rapidly. So this is something you illuminate a metallic plate, okay, metallic electrode with light, okay, and you apply a voltage between two electrodes. This one, illuminated one, which we can call a cathode, or because this is the one emitting the electrons, or the emitter, okay, and this is the anode, or sometimes it's not actually cathode and anode. This is more the emitter and the collector. Part of the electrons, they pass through this second electrode, and they can be detected at the end, okay, of the glass tube as a current, okay, an electronic current. And so you basically you measure the current as a function of the frequency and the intensity of the light, and also as a function of the value of the voltage applied between the two electrodes, okay. And so why is it so important in physics and in modern physics? This is the beginning of the modern physics. It is because Einstein explained what is observed, okay. Here, for example, you already have these slides, okay. The principle is, I will remember you have this voltage, okay. So electron with negative charge, they are accelerated positively, so their velocity increases if the voltage is positive, and so you will have an increasing in kinetic energy, and you will detect all the photoelectrons. If the voltage applied is negative, so you will have some of the photoelectrons that will come back, okay, before passing this collector, okay. So they won't be detected, okay. So you have a diminished photocurrent, and so this is all okay. The problem is when you study as a function, for example, and you have what is called the stopping potential, okay, which is called V naught, okay. This is V naught is positive, so this is the stopping potential, and so for the voltage equal to minus V naught, what you have is that even the fastest atoms, electrons, okay, photoelectrons, they will be stopped before reaching the collector, okay? And so you won't detect any photocurrent, okay? And so everything is very well understood. What is expected in this characteristic curve of the photocurrent as a function of the voltage applied from negative to positive voltage. If you increase the intensity of the light, you have more photoelectrons, so you have more photocurrent, okay, this is okay. The problem is that you expect that as you increase the intensity of the light, you will increase the maximum kinetic energy of the photoelectrons. And so if you increase the kinetic energy, you should increase also the stopping potential, okay, where even the fastest are stopped. And so this is what you expect. So I guess in the slide I won't do that, but here I can do it. So this is not what we observe. This is what we expect. And what is observed is this one. So this is very strange because even if you increase, okay, the intensity of the light, everything is okay, but you don't increase the maximum kinetic energy of the photoelectrons, okay? So it doesn't depend on the intensity of light. More surprising, or as surprising as this feature, you have the dependency with the frequency of the light. It shouldn't depend on the frequency of the light, okay? And you observe something, the saturating photocurrent, okay, for positive voltage, okay, depends on the frequency. And what depends on the frequency here is the stopping potential, meaning that, for example, for this frequency, you have maximum kinetic energy of the photoelectrons, which is higher than this one, okay? So the maximum kinetic energy, the kinetic energy of the electrons depends on the frequency. This is very strange. And also you have a threshold, okay? A threshold frequency. If you have the frequency of the light less than this threshold frequency, you don't observe any photocurrent, okay? So this is very strange. And classically, at the beginning, when people were studying this effect and trying to interpret it as a classical effect, and so they thought that maybe you don't have, well, it was not really as a function of the frequency, it was more as a function of the intensity. The idea was that you had to expect, for example, here, you had to expect some time to accumulate energy to extract electrons from the electrode, but you don't have to wait, okay? If you have a photoelectron, it is instantaneous, okay? You illuminate, you have a photoelectron, or you illuminate and you don't have, and you will never have one, okay? So what is the interpretation of this? Einstein generalizes, okay, the idea that you have a quantum of energy associated with the oscillation, okay, of Planck said it was the oscillation of the oscillators in the walls, okay, of the black body. And I'm recording. And he generalizes this, saying that the light itself is quantized, okay, and we call it now photon, okay. This is a quantum of light, and the energy of a quantum of light is proportional to the frequency of the light, okay, and the proportionality constant is the Planck constant. This is not the first time we see something like that, but let me show you here. You have the energy, okay, which is something associated. This is the energy of the photon, okay. So you have, let's say, a particle, okay. The photon is a particle. a particle of light. Okay, here you have a quantity, the frequency, which is typically associated with the wave-like, okay, phenomenon. So this is a wave, okay, and so we will see later other relationships like that between the behavior of a particle and of a wave, okay, and generally what is between the two of them, what correlates, okay, these two kind of behavior is the Planck constant, okay, so keep it in mind. This is quite important, okay, and so what happens? You have the energy of one photon, which is completely transferred to one electron, and you have here, this is the equation of energy conservation, okay, the energy of the photon, which is here, okay, you have the energy of the photon, okay, is used by the electron to have the electron removed from the surface. So this is the work function, okay, so this is the energy you have to give it to give to the electron, so as to take it out of the metal, okay, and what is remaining of the energy is used as a translational energy, which is the kinetic energy, okay. So this energy of the photon is used to extract the photoelectron and to give it energy. And what is HFT, which is the threshold, okay? It is when you have only the energy, okay, sufficient to extract the electron, okay, with no plus zero, okay, no kinetic energy, because it just has the energy to get out of the metal and no more. So this is the threshold, okay? So with this interpretation, you describe everything of the photoelectric effect, okay? So this is, again, this equation. EV0 is the work, okay, of the electric force on the electron, okay? And so this is the energy, okay, equal to the maximum energy, okay, and it is equal to the energy of the photon minus the energy necessary to take the electron out of the metal, okay. So you have this is the equation. If you write the equation of V0 as a function, V0 as a function of the frequency here, you have V0 equal to H over E times the frequency, okay, minus phi over E, okay, which is a constant. So you have this straight line here, and the slope here, the slope is H over E, okay. And so you can, these are experimental, okay, measurements, and you pass a very nice straight line, okay, between these experimental points, okay. So here you have these two important quantities, okay, we are already using, we will go on using, and in the new system of units, okay, no international system of units, H and E, okay, the Planck constant and the charge, the elementary charge, they are exact, okay. So we can use this value. There is nothing after that, okay. This is the value of H, and this is the value of E. Okay, here a few examples of the work function for a few metals. Okay, sodium, cesium, cadmium, etc. You can see that they are in the range of a few electron volts. 1 electron volts equal to this quantity. You see, this is the energy. Okay, this is an energy. This is the energy of 1 electron accelerated by 1 volt, okay, of voltage, okay, and so we call it 1 electron volt. The unit, we can do some exercises after that. I think I will, can I do this now? No, I will go on, okay, because I would like to finish with the Compton effect, okay? So, finished the photoelectric effect. We will do some exercises, lists, and homework and things like that, okay? And the idea, what we can say here, for example, can you arrange, okay, let's say I will choose a few one. This one is very small, this is cesium, okay? It's very easy, or is it difficult? What do you say? For a cesium surface to emit photoelectrons, okay? This is easier for cesium and for lithium and things like that, okay, actually, than for, let's say, the worst here is this one, okay? Platinum, okay, you have to use a photon, okay? If you want to extract 1 electron from platinum, you have to have a photon with here. What is the threshold frequency, for example, if you want to observe the photoelectric effect on platinum, okay? So you write the conservation equation, Planck constant, time the frequency of the photon equal. It will be used to extract the photon, okay, plus K. And why do we write K maximum? It is because you don't have one kinetic energy, okay? You will have a distribution. And so what we can measure, what we can characterize is the maximum, okay, kinetic energy. So we write it this way. So for the threshold frequency, okay, I will call it F T, underline T. Okay, what do we have? We have the electron is extracted with no kinetic energy, okay? So K max equal to 0. So we have HFT phi, okay? So all we have to do to calculate the threshold frequency here for these elements is divide the work function by the Planck constant, okay? So this is a constant, a positive one, and so you can see that the threshold here will be quite high, okay? I think it would be nice to write it. So we can do it now. Okay, so let me write it here. Okay, the easiest one, cesium. Okay, I don't know why I use the cesium. Okay, phi equal to 1.95. The unit is electron volts. Okay, so we have the threshold frequency for cesium, which will be, okay, remember you, which will be phi over h. Phi over h, okay, it will be 1.95 electron volts, okay. And what we can do here, okay, so this will be a frequency. Here h is short second. Okay, this is energy. Obviously, we will have to. So I will write it. This is 6 dot. Where is the value of h? 6. So I won't write everything. 6.63, for example. 6. 10 to the minus 44, 34. Okay, so if you write with the units, you see you can adjust. You will find something, but the unit will be very strange. Okay, so I want to find a frequency in hertz. Okay, so I will write it times. I want to have something like electrovolts. Okay, poof, poof. Okay, EI. So what is this conversion? This is here, 1 electrovolt equal to this one. Okay, so I will divide by 1 dot 60, okay, 6, 10 to the minus 19. Okay, actually no, obviously not. I have to it would be very weird. 1, 6, 10 to the minus 19. Okay, and so if you calculate, okay, let me. Okay, you have to. This is a few units. Okay, in electron volts, and when you calculate in joule, you have a very small quantity in joule. Okay, so it's 10 to the minus 19, 20. Okay, joule. I will calculate it. 95 times. Okay, so this threshold frequency is 4 points. I will put a 1 here. Okay, 10 to the minus. 10 to the minus. It's a frequency 10 to the 14th hertz. Okay, so this is some frequency. Okay, so what is the color of it? We can calculate wavelength. Lambda is C over Ft equal 6, 7, 10 to the minus 7 meters. Okay, so this is 637 nanometers. Okay, so this is visible. Okay, this is red. Okay, now if we do the same exercise for platinum. Okay, 6. I will just, for platinum, I will just change phi 6.35, and I won't calculate everything again. I will have equal. Okay, I will divide. Okay, it will be I will divide by 195 times 630. Okay, so I will have 15. Okay. I think I forgot 10 to the 14. Okay. Okay. Okay, so it's very... I put with the same power here. Okay, so it's a much higher frequency. Okay, it's probably not visible. And so I don't know. Okay, it's 10 to the 14th. Okay, hertz. You know, it's okay. This is light. Is it visible or not? Is it what is the color? Normally, okay, it's better to go to the wavelength. Okay, it's yeah. Okay, 6. Okay, nanometers. Okay, so this is not in the visible spectrum. This is UV. Okay, and so okay, sorry. Okay, so you can calculate, okay, this threshold frequency for all the elements here or others, okay, and you have this relation, okay. So, for example, you know that glass, ordinary glass, cuts absorbs UV, okay. So, if you put some glass between, okay, on the light illuminating the cathode, okay, you won't observe the effect. Okay, so this is the photoelectric effect, the importance of it being that I remember you that Einstein won the Nobel Prize for this interpretation of the photoelectric effect, the fact that light is constituted of packets, okay, of energy proportional to the frequency, okay? And so now the last part, which is X-rays and Compton effect, okay? To complete this description of the quantization of light and energy, okay? So let's talk very quickly about X-rays. So in 18, at the end of the 19th century, okay, this guy, Röntgen, discovered accidentally, okay, the X-rays, and they were observed actually in the same kind of arrangement, okay, experimental arrangement we have already studied. Okay, you have two electrodes, and so you apply high voltage between these two, and you observe. Okay, here you have a metallic. Okay, this is tungsten, probably from the original apparatus. Okay, and so you can observe the emission of rays. It's something they didn't really understand what it was, so they called it there. I don't know if it's there or if it is Röntgen, but he called it X-rays. Right? And so what he could observe is that there was these rays, they were not detected by deflected, sorry, by magnetic fields, okay? And they were observed actually with, let me come back here to the photoelectric effect. Okay, the photoelectric effect, this apparatus here. You have some material here, okay, and so the electrons, the cathode ray, okay, particularly in the Thomson experiment, okay, so they are stopped, okay, stopped by the glass, for example, okay, and this was accompanied sometimes. They observed this was this rays, okay. The electrons which are not collected, they are stopped, okay, and so they deduced from some this behavior, for example, that it was probably an electromagnetic wave caused by what is still today called Bremsstrahlung. Okay, this is a German word meaning the radiation. Okay, caused by braking. Okay, the brake in the sense of the contrary of accelerations. Okay, so you have some electrons. Okay, so they have some kinetic energy and very in the target. Okay, they are stopped. Okay, and so there are charges. Okay, and so when they are accelerated positively or negatively in this case, okay, they will emit electromagnetic radiation. So they thought it could be something like that, okay, but they couldn't observe. They couldn't observe. It doesn't mean that there was not refraction, okay, or interference, okay. How do you characterize? Okay, we will see. This is you have some phenomenon and you don't know if it's is it a particle, is it a wave, okay. So if you want to be to know if it is a wave, so you make some interference or diffraction experiment, okay, because wave interfere, okay, and they couldn't observe anything like that with these rays, okay, but they could observe diffraction, okay. When you pass some this, you put some slits, okay, to direct a beam of these rays, okay, and they could see that you have diffraction, okay, if you pass some beam, okay, through a very narrow aperture, you will have diffraction if it's a wave, okay. You studied this in physical optics, and so they could measure some kind of wavelength for this electromagnetic wave, which would be like here. This is okay, 10 to the minus 10 meters. This is very small, and so von Lauer, I think this is von Lauer, at the beginning of the 20th century, he said, well, this is the wavelength is of the same order of magnitude that the distance, okay, if you have a crystal, okay. So you have the atoms, for example, it's an atomic crystal, these distances, okay, you can call it. Okay, so it's solid state physics, you have different configurations, okay, but these distances, they are of the same order of magnitudes of the, okay, a few 10 to the minus 10 meters, okay, they call it angstrom, okay. And so it would be a nice diffraction grating for these X-rays, okay, to really check, okay, if this was an electromagnetic wave of wavelength of this order of magnitude. So he did the experiment, okay, X-ray diffraction. So what is the experiment? You have your X-ray, you have a crystal, and you will observe, okay, photographic plate, okay, to which will have bright points, okay, and this is a photographic plate with Lauer spots, okay. This is still today, okay, a very meaningful way to characterize the crystalline structure of the crystals. Okay, so you use X-rays, you make the diffraction of these X-rays on the structure of your crystal, and you analyze the distribution, okay, on your photographic plate or detector, okay, and so you can deduce from what you detect, okay, what is the arrangement of the planes, okay, the planes of the atomic distribution inside the crystals, okay. At the same time, the same period of time, okay, in the beginning, actually the same year, Bragg, I didn't write here the name, the first name of Bragg, because I think there were two Braggs, okay, the son and the father, and they did this experiment of Bragg scattering, okay, we still call it like this. So what is the experiment? You have a crystal, okay, so this is a scheme of the arrangement of atoms in your crystal, and so you have, okay, this distance. You select planes, okay, I didn't copy here an image of this solid state illustration figures, you know, where you have the different structure, cubic structure, centered cubic structure, and things like that. So you have atomic planes. So this is very schematic, two planes, a family of planes. So you have a lot of planes, okay? You don't have two, then you have another one here, another one here. And the distance between these planes is d, for example, in this case, okay? And so what you observe is that you illuminate. This is your X-ray here, okay? And this ray will be scattered by the planes, okay? The first, second, all of them. And so what you will detect here, you will detect, as they are electromagnetic wave, you will detect the result of an interference, okay? Because they will interfere. So they can interfere constructively or destructively or in between, okay? And so obviously you have also, okay, this one. You have all of them, but essentially you will observe the interference between these two. The description is sufficient with these two first planes, okay? So the distance between them is d. In the Bragg scattering, okay, in optics, when you have a surface here, and so you have the normal to the surface, and you have some light incident on your surface, okay? And normally, okay, we have the reflection and we will have the refraction, okay? And so in optics, we usually call this angle here the incidence angle, okay? And this is the reflected and this is the refracted or transmitted angle, okay? So this is optics. Here to describe this scattering, okay, by the different planes, we call theta, okay? Theta is the complementary, actually, okay? You see, this is this angle, okay? So this is pi over 2 minus this incidence angle in optics. Why am I telling you this? Because I made some mistakes, okay, in my life, okay? If you don't pay attention to this kind of details, you have some very weird results, okay? So this is theta. And so what is the difference of path, okay? Delta will be the difference between the two paths, okay, the distances. So this one is refracted and directly, okay, incident here, and is directly scattered. And this one will have this distance plus this distance, okay? And so this is what I call the path difference, delta. And you can see that it is 2 times this distance and this is 2 times d, okay, sine of theta, okay? So, okay, I wrote it, and so, independently, okay, this is an interference problem, this is a wave, okay? So if this difference, this path difference here is integer, okay, m times the wavelength, okay, so you will have a constructive interference, okay, constructive interference, and if it is m plus half, okay, lambda or a number. Oh, yes, I can write it like this way. Okay, so integer plus half wavelength, so this will be destructive. Okay, so what you do, you vary, okay, this Bragg angle. Okay, this is the Bragg angle, and so this is the Bragg condition. What is the Bragg condition? It is for constructive interference, meaning you will detect something, okay? Destructive interference, you will detect nothing. Interference. Okay? So this is the Bragg condition. This is very useful. And this is why I insisted on the fact that this theta is this angle. Okay? And so let's see, what do we observe? Okay, actually, we will come back to X-ray after, okay? I needed to write this Bragg condition because we will use it, okay, now for the Compton effect to explain how the experiment of the Compton effect was interpreted, okay, and was measured, actually, okay? So I won't show you now an X-ray spectrum, okay, but it's very interesting, okay, but we will come back later on this wave X-ray spectrum, okay. So what we are going to study now, this is the Compton effect. The Compton effect is very important because it is really, Einstein says, oh, the photon is a particle, it has an energy, okay? So you students of engineering, okay, sciences and things like that, you remember then when you study collisions between particles, okay, you have some equation of energy conservation, okay, and depending, okay, for example, an elastic collision, okay, you have conservation of the kinetic energy, but you always have the conservation of energy, okay, in general, and you have the conservation of the linear momentum, okay, and so, okay, what is the linear momentum of these light particles? You remember that in mechanics, okay, you have the linear momentum, which is the mass of the particles times its velocity, okay? So we said the photon is a particle, it may have a linear momentum, but its velocity is c, and actually we will see it doesn't have mass, okay? The mass of the photon is 0. So let's see here. What is the Compton effect? Okay, I'm talking about the Compton effect, but I didn't describe it. Okay, so the Compton effect, you have some X-ray tube, okay? The X-ray tube is what we already saw, okay? It's something where you have a discharge, an electronic discharge creating an X-ray beam. You select a direction for this beam, okay? So you have your X-ray here. Let me put it in red, okay? So this is X-ray. Okay, you have your target. Okay, and so you will study the uh, the scattering. Okay, of this. Actually, this is a foil. This is a very thin foil. Okay, this is not a very good. I prefer this one. Okay, so you have your X-ray source. Okay, this is the tube. Okay, and you have your incident X-ray beam. Okay, you have your scatterer. So it is usually a very thin. Okay, a foil of metal. Okay, and so you have the incident direction. Okay, if there was no if there were no scattering here, and you will observe what is scattered in directions different from of theta here. Theta equal to 0. This is the incident direction. Okay, so you vary this theta. So you put it. You will have some detection. And how do you detect? And particularly, you want to detect the wavelength of this beam, okay, scattered. And so you use this configuration of Bragg, okay, because Bragg, you have a relationship between the angle, okay. Obviously, you have to know your crystal, okay, so you know it, okay, and so you vary, okay, your angle, you detect, and so you can deduce what is the wavelength of what you are measuring. Okay? And so this is only the part of detection here. What interests us is the following. Okay? So you have here this horizontal axis here is the wavelength, lambda. Okay? In angstrom. It was very, we don't use angstrom anymore, but it was, okay, 10 to the minus millimeters. Okay? And so this is the primary, theta equal to 0. So this is the same direction. This is this direction. Yeah, okay, this direction, theta equal to 0. So after that, you increase theta, okay, 45 degrees, 90 degrees, and you can also have angles, okay, higher than 90 degrees, okay, here 135 degrees, okay? And what do you observe, okay? You see that this peak here, the wavelength is this one, okay? So this is the original one. I will call it lambda 0, okay? So you have your, this is lambda 0, okay? And so you will detect something which is lambda 1, okay? And so this lambda 1 is this one, okay? So for theta equal to 0, we don't see it, but you can see here that it appears a second peak here for an angle, increasing angle, okay? And the distance, the difference between lambda 1 and lambda 0 increases as you increases the angle, okay? This one is always here, obviously. This is the primary, okay, beam. And so you have this one. And so this is very strange, okay, because what is known at this time, the Rayleigh, I think it was known already, you can have a scattering, okay, but you won't have a difference. The wavelength will be the same, okay, as the incident one, okay. And so what is this Compton effect, okay? So in the Compton effect, what you measure, this is this distance here. Let me see here, lambda 1 is higher, okay? You see here, lambda 1 is bigger than lambda 0, okay? And this is a function of, I won't write f because It seems like it is of the frequency. I will call it G. Okay, G of is a function of the angle. Okay, and so you measure this distance, which is called delta lambda, as a function of the angle. Actually, we will see it is cosine of theta. Okay, so let's see. Okay, we will do it here. Okay, you have the Compton effect is important because it is interpreted, okay, as a collision between two particles. Okay, so this is very strange. Okay, the particle of light, okay, and an electron. Okay, so the particle of light is the photon. Okay, so it is an X-ray. We will see later what it has to be a photon from an X-ray. So it has an energy E0. Remember, E0 is the energy of a photon. Okay, so this is H times the frequency. Okay, this is the quantum of energy. Okay, of light, the photon. Okay, and so it will collide. Okay, you have this. Here, this is an electron. What I showed before was a target, okay, a scatterer here. This is a thin foil. What happens is that the energy of the X-ray, of the X-ray photon is very, very high. And you can really, really neglect the work function, for example, okay, to extract the electron from the metal because it's a few electron volts, okay, and so you have energies, okay, which are very, very much bigger, okay, and so if there is a phi, okay, it is really, really smaller than h f0, okay, so we don't take it into account, and so the collision is described as a collision between a photon, okay, and an electron at rest. Okay, it doesn't have any velocity because it doesn't change a lot of things. Okay, this velocity is very small. Obviously, it's not completely at rest, but we can model it as if it was at rest. Okay, so a photon and an electron at rest. Okay. And so we will apply, you already know how to do that, okay, from classical mechanics, okay, you will apply the momentum conservation equation, okay, and so this is a two-dimensional problem, okay, you have xy here, and so this is before the collision, and this is after the collision, and so what do you have after the collision? The collision, the two particles, okay, the photons goes another way, okay, and the electron is acquires some kinetic energy in some direction, okay, and so theta is used to describe the direction of the scattered photon, okay, and in the Compton experiment, this is what we measure, okay, and the electron is scattered in another direction, okay, characterized by the angle phi, okay, and so we write first the momentum conservation. Actually, you know, this is a vectorial, okay, so you have p before equal to p after, okay. Before, you only have the momentum of the photon because the electron is at rest, okay. After, you have the two momentum, okay, so we write it this way. Before, this is p naught, okay, the momentum of the photon before, okay, and after we have, so this is on the x axis, okay, and this is on the y axis. We have two equations, okay. This is one vectorial equation, and these are two scalar equation on the two orthogonal axes x and y, okay. So on the x axis here you have, what is the momentum? You have p1, okay, the new momentum of the photon, p1 cosine of theta, plus, okay, p, we call for the electron p cosine of phi, okay. And on the y axis we have p1 sine, okay, of theta, and here minus, okay, sine of phi for the electron, okay. Okay, so actually this is, before here is 0 equal, okay, before, no, there is no momentum on the y-axis, so this is 0, okay, and this is now, okay. So you have these two equations. So these are the two equations. What is important here is that we have two things, okay. We have to treat it with the relativity, okay. P0, okay, this is the momentum of the photon. And so it is actually equal, or maybe I will explain it here. You have, yeah, I said I would explain it. Okay, page. Okay, the relativistic energy, okay. So you have the relativistic energy. Let me find here, I have a piece of paper, okay, where, yeah. You have a particle, okay, for particle of momentum p and velocity v, okay. So I will have to post, okay, this video on the relativistic energy, but we can show that the total energy is called E, okay. And so you have this equation, E square equal to C square P square, okay, plus okay. So this is relativistic energy, okay. So this is total, okay, and it has two contribution. This is the kinetic energy, and this is the rest energy. Okay, so the fact that you have a mass, so this is the rest mass, okay. So you have energy, okay. The mass is a form of energy, so you know E equal to mc squared, okay, very known, but actually it's a little more complicated. If you have some particle at rest, okay, particle at rest, what is the relativistic energy of a particle at rest? Okay, this is the energy. Okay, and so for the photon, what you have? The velocity equal, let me see here. Yes, there is something. Missing here, okay. What we have also is this total energy. Total, I already wrote it, so it's E is equal to okay, where beta, okay, we saw it, okay, when we studied relativity, okay, so this is actually, it's better maybe to put it this way, v square over c square, okay. So you see, it depends, the energy depends on the velocity of the, so you have two ways we can, okay, this is the same. We can show that it is the sum of the kinetic and the rest energy, but we can already write it this way, okay? And so, as the photon, okay, the velocity is c, okay, in vacuum. And so you have the energy of the photon, okay, which is zero. What do you say? Is the energy of the photon infinite? It's not. So for the photon, we use this expression here. Why can't we use it? There is no problem actually. Okay, why is there no problem? You divide here by 0, but you also have 0 here. Okay, we will see m0 equal to 0. Okay, so you have, okay, we know that E equal hf. Okay, we know it, Einstein. For a photon, okay, I'm speaking of a photon. Okay, and so you have E square equal to C square, E square, okay, and the photon has no mass, okay. So what is the relationship between the momentum and the energy? P equal E over C, okay. P equal to hf over C, it's equal to h over lambda, okay. And so we will use this definition, okay, of the momentum for the photon, okay, in our description of the collision. I only want to remind you what I said at the beginning of this lecture. Oh, what do you see here? This is a quantity related to particle, okay. Here, this is a quantity related, well, energy is not really, but we'll take this one and this one. This is a quantity related to wave, okay? And what is, okay, what relate the two behaviors, the particle one and the wavelength one? This is the Planck constant, okay? This is the second time we see it, okay? The first time was the E equal h f, okay, wave, particle, Planck, particle, wave, Planck, okay. So going back here to our equation, so I write for the incident photon P naught equal to h over lambda naught, okay, P1 after, okay, it's h over lambda 1, okay. So you can understand, okay, I will. And so the other equation you have to, so what do you know here? You don't know exactly what. Okay, I won't solve this system of equation. Okay, I just want to. We have three equations. This one. Okay, this, and this one, which is the conservation of total relativistic energy. Okay, so now you know everything about relativistic energy before, after, okay? So what is the total relativistic energy before the collision? You have the energy of the photon, E naught, okay? and you have the relativistic energy of the electron. It is at rest, so it is mc squared, okay? This is the mass of the electron, okay? And this total energy is equal to the total energy after the collision. So you have the energy of the photon after the collision, the kinetic energy of the electron, okay? Here it was at rest, here it's no more, okay? And it still has this rest energy, okay? And so you have this term here and here. So actually what you have is E0 minus, or E0, minus E1 equal to K, okay? And so this is very normal, okay? You have a collision between two particles, okay? And so you will, why do the wavelength of this photon increase? Compton effect. The wavelength of this scattered photon increases, okay? It's bigger than the incident one. It does because the energy of the photon, okay? If you increase the wavelength, you decrease the frequency, you decrease the energy of the photon, okay? And so where has this energy gone? It has gone as kinetic energy of the electron, okay? And so when you write, you solve this system of equations, okay? I won't do that. So what you find is the Compton equation, delta lambda, okay, which is the difference, okay, I can write it here as lambda 1, okay, minus lambda naught, okay, and this is h over mc, this is the mass of the electron, okay, this is a collision between a photon and an electron, times 1 minus cosine of theta, okay, and this is sometimes called the Compton wavelength, lambda c, okay, it's not a wavelength, okay, there is no wave associated with this quantity, but it has, this is no dimension, okay, this is a number, 1 minus cosine of theta, okay, so this is wavelength, so this has the dimension of the wavelength, and it is called the Compton wavelength. H is a constant, Planck constant. The mass of the electron, you know it, it's 9 something 10 to the minus 31 kilograms, okay. C is on the order of 3 to the 10 to the 8, okay, meter per second. So you calculate it and you will find that this Compton wavelength, this is a constant, okay, which is in the, let me show you here, in the table of constant, okay, this is 0.00243 nanometers, so it is very small, okay. And so just to show you here, fundamental physical constants, where is the Compton, okay, here, Compton wavelength, okay, this is a constant, lambda c, and this is 2426, blah, 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 blah. This is not an exact value because the mass of the electron is not exact, okay? C is exact, H is exact, but the mass of the electron is not, okay? And so when you see that, when you increase, okay, let's analyze now what was observed, okay? I will put another page here. So you have lambda okay, minus 0 equal lambda c 1 minus cosine theta, okay, so theta equal to 0, okay, cosine theta equal to 1, okay, lambda 1 equal to lambda 0. Okay, there is no difference, okay, in the wavelength. Okay, if you increase theta, okay, so you will decrease cosine of theta, okay, and so 1 minus cosine will increase, okay, and so you will have, okay, 1 minus cosine increases, okay, and so delta lambda increases, okay. This is what we observe on this, okay, things you increase, okay, and what did I want to say about it? There was something I wanted to say. Okay, so okay, I remember. Why do you need X-rays? Okay, why is it better to use X-rays to observe this effect? Okay, this is something like 10 to the minus. We saw it's 10 to the minus. What is the value here? Okay, so this is nanometers. This is 10 to the minus 9. Okay, minus 10, minus 11. Okay, minus, I will stay here. Okay, this is in 10 to the minus 10. Lambda c is the order of magnitude of lambda c is 10 to the minus, what did I say? Right. 10 to the minus 9, 10, 11, okay, unit, 12, okay, 12, pico, 10 to the minus 12 meters, okay, this is picometer, okay, so this is very small, okay, cosine of theta, okay, varies between minus 1 and plus 1, okay, so you will have something, okay, cosine of theta between minus 1 and plus 1, and so you will have 1 minus cosine of theta, which will be between this one here, 0, and this one here in 2. This minus this will minus 1. Okay, so this is it, no? Minus cosine is okay. Minus 1, 1 minus cosine. Sorry, this is between. Yes, okay, that's it. And 0. Okay, so this is very small value. So this difference here will be very small. Okay, will be on the order of 10 to the minus 12 meters. Okay, so if you have a very big wavelength, okay, a small frequency, you won't observe. Okay, if you have something like visible light, okay, visible light, okay, lambda of the order of 100 of 500 nanometers, okay, so you will have some delta lambda, okay, which will be of the order of 10 to the minus 12, okay, this is 5, 10 to the minus 7, okay, and so you have 5 orders of magnitude between the two, okay, so you won't observe anything with visible or even UV light, okay, so you have to go to X-ray, okay, with very, very small wavelengths. Okay. Okay. I will stop here. Do you have questions?
É, eu queria. Eu entendi a questão do efeito Compton, mas eu não entendi. Eu estava lendo aqui antes, aí eu vi que ele estava lendo assim bem por cima. Tá? É, no caso, o desvio de energia do feixe, né, vai depender do elétron